Okay, so in section 8.5, we're going to work with a concept called partial fractions. And I have a note at the bottom of your in your page and at the bottom of this screen. And I'm going to actually start with the note. Okay, so pause with me, don't write anything down yet, but I want to read this note to you. Partial fractions is actually a college algebra topic. Okay, but it isn't usually taught in college algebra. That is to say, it's in the college algebra textbook, but it's not usually a topic that we sort of strive to get to. Because, believe it or not, the majority of our students in college algebra aren't going to take Calc 2. It's shocking, isn't it? Like, why not? So it's actually a concept that you usually encounter when you get to Calc 2. I encountered it in Calc 2. And I had a really good college algebra background, you know, everything up to Calc 2, and I still encountered it in Calc 2. So it is typically taught in Calc 2. I have known one student at one point in time in a college algebra class that actually taught partial fractions. So the point of what I'm saying is that everything leading up to the actual integration with what we were doing is not calculus. But we've done a lot of problems like that, haven't we? Long division, it's not calculus, yeah? All right, so go ahead and fill in some of these details. What we're going to be doing is we're going to be doing decomposition of fractions, i.e. that's why it's called partial fractions. So if we call the numerator n of x and the denominator d of x, well, the first thing we have to do is long division if we need to. So how do we know if we need long division? Well, we need long division, and we've encountered this before, when the degree of the numerator is greater than or equal to the degree of the denominator. So if, in fact, that happens, first step, long division. Okay? And you've done that before. The second step, or if you don't have to do the long division, it would be the first step, would be to factor the denominator. So we factor our denominator. And then we write the denominator as a bunch of separate fractions with those different factored pieces of the denominator. That's step 3. Step 4 and step 5, I'm just going to let you write them down. Almost everyone's done writing. These problems are a bit different, and they're kind of fun, so we'll see what you think. So we're taking a look at the first one. Very clearly, the numerator does not have a degree bigger than the denominator, right? Or equal to, so I don't have to do any long division. So everybody raise your hand if you're thankful for no long division on the problem. Okay, I thought so. The other thing that you might want to look at this, and you really should pause and look at this and say, now wait a minute, is that this denominator looks kind of like the arc-trig functions we were dealing with, doesn't it? We did arc-trig functions, and we had different pieces of things squared. We even had some square roots when we did arc-trig functions. So at the point when you get one of these problems, it is valid and reasonable to look back and say, is that one of those arc-trig functions? Because if it were, that'd be good. And we wouldn't have to do anything else, right? Because it would fit one of those forms. If you check one of those forms, there is one that has no square root and that has a squared piece of each of the pieces in the denominator. However, the denominator is addition instead of subtraction. So this does not fit one of those forms. Okay? So we do not have a form until now to be able to deal with this particular integral. What we can do right now, though, is we can factor that denominator, and that is our next step. So what is the factorization of that denominator? How can I factor 4x squared minus 1?
2x.
Right. 2x plus 1 and 2x minus 1. So I know you thought factoring was just for sissies in college algebra or something like that, but it's really useful because you need it. You have to be able to factor in this section, okay? And this is a difference of squares, and so it factors exactly the way Cameron said. The 4x squared becomes 2x and 2x at the beginning of each of the parentheses, and then the negative 1 at the back becomes a negative 1 and a positive 1. And it needs to have that form because if you take a look, then the inside and the outside terms add to 0, right? Because they are the exact same with opposite signs. One's positive 2x and the other one's negative 2x. So this is the proper notation. So here's what we do next. Okay, so this was part 3. It said write as 2 separate fractions. So in this case, it's 2 separate fractions because there's 2 separate factors in the denominator. So I have a 2x plus 1, and I have a 2x minus 1. Now, I do not have ones on top of those, but I do have to figure out what I do have on top of those. And that's the partial fractions part of what we're discussing here, okay? So I need to write each of them, and this is step 4, with a degree 1 less than the denominator. What is the degree of each of these denominators? 1. So a reminder, a degree is the highest exponent. I just have the exponent x to the first. So this is a degree of 1. So what would something look like if it had a degree 1 less than 1?
0.
Degree of 0. Degree of 0 actually means that I have a constant. That is, I have simply a number. There will be a number, and I don't know what they are, so for the moment, I write them down as A and B. There will be a number on top of each of these because a degree 0 polynomial is actually something that's just a constant. Okay, everybody good so far? What I want to do now is to do step 5, which is to reconcile this new fraction, 2 new fractions that I just wrote down, with the original fraction that I started with. And you might say, what does that mean? Well, in essence, what it means is I need to take these 2 fractions and I need to multiply them back together, like you back did, in I don't know, 7th or 8th grade when you were working with fractions and you actually pushed them back into the same fraction together and multiplied them. And that means common denominators, right? All right, so what I'm going to do over here is I'm going to actually work, and I'm going to pause my problem of integration for the moment. Okay, so I'm going to hit pause. And everything I'm going to do, I'll do it on my left-hand side of my screen. Everything I do on the left-hand side is going to be the algebra portion. It doesn't continue with the equals of what I'm working on, okay? I need to figure out what the next step is going to be. In other words, I've got to figure out what A and B are. And the way that I do that is I actually multiply my fractions together. So if I were to multiply these fractions together, I'm sorry, not multiply them together. Yeah, I said it right. Multiply them together, combine them to get a common denominator. I would need the denominator that's not there. So I need to combine the fractions. I need to add them together, and I do that by getting a common denominator. And a common denominator will be the exact denominator I started the entire problem with, which is the multiplication of each piece that's missing. Okay, so far so good? Now I'm going to distribute out that numerator. So I have 2ax minus a plus 2bx plus b over 4x squared minus 1. And what I know is that this fraction has to equal this one, which means all of that mess on top, 2ax minus a plus 2bx plus b, has to equal the number 1. Okay, everybody with me? Okay, so this expression right here on top, this has to equal, has to equal the number 1. Now in particular, it's not just the number 1, it's actually 0x plus 1, because I don't have any x's either, correct? So what I really want is I really want 2ax minus a plus 2bx plus b to equal 0x plus 1. And what that means is that all the terms with x in them have to add up to 0, and all the terms with just a constant in them have to add up to 1. So I'm going to take this expression and we're going to go to the next page. All right, that is not what I wanted. Let me try again. I'll just rewrite. All right, so the terms that have to match up are the ones that actually have the variable in them matching or don't. So those 3 pieces all have x in them. So that means that 2a plus 2b have to equal the number 0. Are you with me? Because the 2a and the 2b have to add up to 0 so that I do not have any 0 x's when I combine them in my problem. Furthermore, the pieces that I haven't marked yet, which are negative a and positive b, those have to add up to the number 1. So negative a plus b has to equal 1. Well, this looks even more like college algebra because you have 2 equations and 2 variables, and you need to be able to solve them. And you have 2 methods that are sort of the most overarching methods, the most common methods from algebra to do that with, and that is either substitution or elimination. Do you remember those methods? So elimination, or sometimes it's called the addition method, means that you stack them up so that you add them together and one of them goes away, which I could do really well with this one. Or the substitution method means I solve one of the equations for either A or B and I substitute it into the other equation, which I could do really well with this equation as well. I'm going to do this one with elimination just because it's so clean and nice. If I take that equation that's 2a plus 2b equals 0 and divide everything by 2, I get a plus b equals 0. Okay, and that's the general idea of what you do when you do elimination. You either have to multiply, usually have to multiply or divide one or both equations by a number. And the reason I like this is because if you take a look then, I have a negative a and a positive a, and what happens when I add those together? I get 0, right? They go away. But then I have a b, and that actually becomes 2b. And I have a 1 and a 0, and that becomes 1. What does b equal? 1/2.
That means we want to do matrices.
You can do matrices if you'd like to. That's fine, Cameron. Matrices work too. They're not really something that probably most of you have done a lot with, which is why I didn't bring them up. But if you want to do a matrix, you could do a matrix. That's fine. All right, now A has to be a number that adds to B and gets 0, because I know that A plus B is 0. So what number does A have to be? A and B add to 0. Negative 1/2. A and B add to 0, right? So if A is 1/2, if B is 1/2, then A is negative 1/2. These 2 pieces of information are exactly what I need back on my other slide now. So take again this example, or this integration that we were working with, and I said let's put this on hold. And what I want is I want to replace A then with what A equals, which is negative 1/2 over 2x plus 1. And B with what B equals, which is 1/2 over 2x minus 1 dx. Okay, for real. There we go. Okay, so here's where I am, right? I'm going to separate this into 2 different integrals, and I'm going to pull the 1/2 and the negative 1/2 out in front because I can, right? It's easier to work with, a little bit easier to see. So this is negative 1/2 integral of 1 over 2x plus 1 dx, and then plus 1/2 the integral of 1 over 2x minus 1 dx. You okay with that? Now, some of you have done some very interesting things on your basic skills quiz with expressions that look like this, or you've wanted them to look more like this. This does involve logs because I have x to the power of 1 in the denominator. Okay? It's okay that I have a coefficient in front of it, and it's okay that I have the minus or the plus 1 added to it. But what I need to change is I'm going to change this one at a time so that I can actually do this problem and see the logs present. So I'm going to let u be 2x plus 1. And then what would du be? Two dx actually, right? So again, I'm just doing the leftmost fraction here. So I do not have a 2 in the problem. In fact, I have a 1/2, which is just the exact opposite for all intents and purposes. So I need to have another 1/2, namely it'll end up being a 1/4 negative in this problem. And then the integral is 1 over u du. Does everybody see where the 1/4 came from? Okay. 1/2 of it was in the problem, negative 1/2 actually was in the problem right here to begin with. And then I have another half from here. I replace dx with 1/2 du. Okay, so I have that 1/2, I have the original negative 1/2 for negative 1/4. Now the other equation does not have the same u, okay, right? Right? Right, thank you. All right, it does not. So I actually have to call it something else just so that I don't think that the u is the same. I'm going to call it v, or you know what, that doesn't even sound good to me. Somebody used z recently. Let's use z. Make sure you do something, make sure your z doesn't look like a 2. I had to put a line through mine. Or use a different letter, whatever letter you want. If you really want to use v, we could. Okay, so z, again, is the same denominator, 2x minus 1. Not same, but is also the denominator, 2x minus 1. What would dz be? 2, yeah, 2 dx. And so for exactly the same reason here, I end up getting a 1/4 because I had the 1/2 originally. I have another half right here because of this 2, right? Divide by 2. So this is going to be plus 1/4. The integral then is 1 over z, or whatever letter you chose, dz. All right, now you're ready to integrate, right? All right, so what is the antiderivative of 1 over u? Natural log of, yeah, remember that absolute value of u, plus 1/4, and here becomes the reason why I needed to make sure the letter was different. What's the absolute value of 1 over, I'm sorry, what's the antiderivative of 1 over z? Right, right. Absolute value, the natural log of the absolute value of z, and I want to make sure that I see the z and the u differently because I'm going to substitute back in corresponding to those values. So the first one, negative 1/4, is natural log of what? 2x plus 1. And then this 1/4 is the natural log of 2x minus 1. They are different because those denominators were different. Now, one thing that I'm going to do real quick here is I'm going to just rewrite it so my subtraction goes in the other order. That is, I'm going to write my 1/4 natural log of 2x minus 1 first. So, and then minus the 1/4 natural log of 2x plus 1. You may not need to have seen that rewritten to see my next step, but in case you did, I want you to see this. This is actually 2 logs that are subtracted, isn't it? Yeah. I'm going to pull the 1/4 out in front. So I'm going to factor out 1/4. Because the plus c doesn't get involved in this, right? And how do you represent 2 logs subtracted more concisely? With division. So this is 1/4. And then it's the natural log, and then you can put the absolute values together. 2x minus 1 over 2x plus 1 plus my c. Any questions on that one? This is a really different process, right? We haven't done anything like this before. And we're going to try another one to try to get a handle on it a little bit better. The next problem is not quite as long. It doesn't take quite as many steps. But I bring it to you second for other reasons. So first, again, notice that the degree of the numerator is not bigger or equal to the degree of the denominator, right? Okay, so I do not have to do long division on this problem. So I'm jumping into step 2. And step 2 says factor my denominator. So what will this denominator be if it's factored? In fact, let me not write it even like that. I'll write it over here. How can that denominator factor? Okay, close, Cameron, and I think you're about to say the right thing was the x squared, right, Hannah? So pull out an x squared, actually. 2 x's is what you meant, yeah. And then you're left with x plus 1, right? And the numerator is still 4x squared plus 2x minus 1. Now, here's the deal. There's actually 3 different factors in that denominator that you could have. You could have, and let me move this over a little bit because I'm going to need a little bit more space. You could have one fraction that has a denominator of x, that when you multiply them, it has this new denominator, x squared times x minus 1 or plus 1. But you could also have a denominator that's x squared. I don't see the x in here, but it's there, right? X times x, or I have x squared. And I could also have the denominator x plus 1. So this is a little bit different, and it's because I have that x quantity squared. So anytime you have a variable or a portion of a variable, whatever, that's squared in the denominator like this, that's actually a factor, you have to have the variable before it was squared and the variable when it's squared. If it were cubed, you'd have to have an x and an x squared and an x cubed. All of those would be possible factors or possible denominators. Now, here's the other deal. That all of these, I'm sorry, the first one and the last one anyway, x is linear, right? So its numerator is a constant, just like on the last problem that we did. And the same thing for x plus 1 at the end. The x squared in the middle, however, because it has this duplication feature to it, even though it's x squared, I do not need an x in that numerator. I promise I'm going to show you one in a minute where you do have something else besides a constant in the numerator. But because of this x squaring feature, I just need, again, a constant in that numerator. And then the third one also is a constant in the numerator because it's linear as a denominator. Okay? Okay, so now, again, we're going to pause on the, we're going to push pause, and we're going to work on the algebra component of this. So I've got this, and I need to push it back together. I need to combine the fractions back together. And so in order to do that, that means each numerator gets multiplied by what it doesn't have in its denominator. So namely, a over x, it only has one x, so it needs another x to be multiplied, and an x plus 1. The b has x squared as its denominator, so it does not need to be multiplied by an x or by an x squared because it's already there. All it needs to be multiplied by is x plus 1. And then the c has the x plus 1 in its denominator, so all it's missing then is x squared, which takes care of the fraction with the variable x in the denominator. Do you see where all those pieces came from and why I don't have any more pieces than I do? Now, it's actually enough to only look at the numerator because you recognize, of course, that the whole point was I factored this denominator in such a way that it was equal to the original denominator. So it's actually enough for me to not write anything in that denominator and work with the algebra only in the numerator. So I'm going to distribute this numerator out. So I have ax squared plus ax plus bx plus b plus cx squared. If you're with me, say uh-huh. Boy, that was a weak uh-huh, like 2 of you. Okay, good, 2 of you are with me. 2 out of 7. We're going to go with that today. All right. Now, portions of this have constants with it. Portions of this are linear, and portions of this are squared. Agreed? I need to collect all the terms that are squared, collect all the terms that are constants, and collect all the terms that are linear. So I'm going to do the squared pieces first. So these 2 pieces are squared. Agreed? So that means that the a here and the c here, the portions that are squared, have to add up to the value in the original problem that was squared, which would be a 4. Okay. I am definitely shortcutting steps as I do this. If you need to see more of the steps, you can look back at what we did in problem 1 and show more of them. That's okay. But this is in essence what I'm doing from problem 1. I'm just taking the pieces that have squareds in them and I'm comparing it to the squared in the original problem. Yes, Cameron?
Would the b over the x squared be b plus x?
You mean bx plus c, actually. And the answer is no.
Okay.
And the only reason the answer is no is because it is just a multiple of a denominator I already have.
Okay.
Typically speaking, the answer will be yes for your question, and we'll see it in example 3 or C or whatever I labeled it, the last one that we probably won't get to today. Okay. All right. So how about B? I mean not B, but the linear terms. So I have an AX, I have a BX, and they're supposed to be equal to 2X, which means A plus B should equal 2. And that's, well, it is what it is, right? It's the next portion. And then let's use, we'll try it. No, it's the same color. All right, for fun, we're going to use purple. And the last value then is the B here. And that B has to then be the value at the end here, which is -1. Now, that's actually very friendly. I have 3 equations and I have 3 unknowns, but I don't really have 3 very complicated equations or 3 unknowns that are hard to find. Not like in linear algebra, right, Cameron? I don't have a plus b plus c equals 1 and negative a plus 2b plus 3c equals 7 and 4a plus 3b minus 2c equals 4. This is really nice because in reality, I know what b is, correct? B is -1. And if b is -1, I should be able to use that value then to find a, because a plus b is actually supposed to be 2. So if a plus b is supposed to be 2, what does a have to be?
3.
A would have to be 3, because 3 plus -1 equals 2. And if a is 3 back in the red equation on the first part, what does c have to be?
1.
It has to be 1. So the solving of this equation is really clean. And that means I can rewrite this integral over here very quickly. I have -1 over x plus b, I'm sorry, not -1. A is 3. Let's fix that. All right, 3 over x plus b, which is -1 over x squared, plus c, which is 1 over x plus 1 dx. Many of you are fond of what I'm doing next because I see you keeping doing it throughout your work, and I like it as well. So you tend to do this. You tend to like to separate all your fractions. And I think that's good thinking. So we're separating each fraction. And I can pull their constant coefficients in front. Like so. What's the antiderivative of 1 over x? Thank you, Hannah. Natural log absolute value x. The second problem, 1 over x squared, has no natural logs in it. Several of you want to do it. Whenever you see an x in the denominator, you want to do something with natural logs. Natural logs will only work if the x in the denominator is linear. That is, it's x to the 1 power, and this x is actually x squared. So I'm going to take one more step, and I'm actually not going to integrate this one, but I'm going to rewrite it to remind us. If you want to integrate because you've already thought it through here, that's fine. But to remind us that this is x to the -2, and I've got a power rule to be dealing with here. Now the next component actually does have that linear x in the bottom, so it actually is a natural log as well, and it's the natural log of x plus 1. And since the coefficient's 1, I don't even have to divide by anything, and I do need a plus c. Now, that does mean that I'm almost finished, very, very nearly. Okay, so here's where I am. And I can actually then do natural log absolute value x. What is the antiderivative of x to the -2? So I'm going to take one step to write it. X to the -1 over -1. And then that will simplify, of course, to what? The middle part. What is the negative? X to the negative 1 over negative 1 with a negative in front of it. What is all that? Okay, first, is it a plus or a minus?
Plus.
It's going to be a plus. And then what? I don't want to write it with a negative exponent.
Okay. 1 over x.
1 over x. There we go. So this is plus 1 over x. And then I have this natural log x plus 1 at the end. Is there anything that I could combine? That was a rhetorical question. What can I combine?
The ln's.
The ln's. But I can't combine them exactly like they are because this one right now has a coefficient, right? So the coefficient has to become an exponent. So this becomes the natural log of the absolute value of x cubed plus, let me write the next natural log where this is too, just to put them together, and then the 1 over x at the end. And then I can combine them. So I can combine them with what? What operation? Multiplication, because they're currently added together as logs. So this is the natural log of x cubed times x plus 1. And then I have plus 1 over x at the end plus c, and I can't combine the 1 over x with this. Okay. I think we did all right on that. So there we go.